My name is Jorge Fernandez, and this is my static analysis project. So I went ahead and decided to choose this sign. It's a regular sign of where I work. It's attached to a 2x6 by this bracket system right here. It's pretty simple, nothing too complicated. So this is a free body diagram. This bottom one is just to show over how the force is distributed, but this is the important one. So this is the Y, the X. We have a front view, which is pretty not really doesn't really matter. And then we have a side view right here. It goes ahead and shows you the wind due to the force, the moment due to that wind, the weight, the reaction, the Y due to that weight, the reaction moment, and the reaction in the X. Right here, this is just a 3D model I went ahead and did just to further illustrate exactly how this bracket system works and how the sign works. So everything is not exactly to scale, but it's pretty close. So like I said, it uses this bracket system with rails attached to the sign, and then there's a 2x6 that goes along this gap right here between those brackets. Inside of those brackets, there's just some screws that drill into the 2x6 to go ahead and provide some restriction of the movement. But other than that, it's just a simple sign, and that's exactly how it works. So now moving on, the knowns and the unknowns. Well, we know that the weight of it is around 50 pounds. It's not too heavy. I've lifted them myself before. It's not that much heavier. So the dimensions of the main sign, I went ahead and estimated. I didn't get an exact measurement, but it's an assumption, and it's pretty close. So it's in length, it's 5 feet. The width of it is about 4 inches, and the height of it is 2 feet, give or take. So now, in order to calculate the force of the wind, I went ahead and looked on and found a line which the website will be referenced in the end. So it's just the simple force is equal to max times acceleration. So in order to find the mass, you actually find the density of wind. So this is the density of wind at sea level. So although we're not at sea level, it's pretty close. So it's the density of sea level times this is the area of the actual sign. So this is I have it in meters here. However, I ended up converting it down here to 3.619, as you can see. So like I said, it's the density times the area of the sign, which actually gives us the mass of air that's actually being applied, and then we just multiply it times the acceleration. So this is just the wind velocity, and then squared. So now, for the equations, all we're going to need, like I said, is summation of the forces in the x, summation of forces in the y, and summation of moments. So there's no z because of how the restraining system is in place, since nothing really restricts the movement in the z direction. There's no reaction force, and there's no force being applied in the z direction either. So we're only using these three today. So in order to solve, as it says here, it's actually really easy to see, as back here, that both the x and the y is just a simple, well, the force due to the wind is going to be the exact same, but equal and opposite as the reaction x, and the weight, or the reaction y, is going to be equal and opposite to the weight. So that's pretty self-explanatory. So you go ahead and reaction x, reaction y is equal to, well, 3.61 negative, of course, and then the reaction in the y is 50, take into consideration that the weight is actually negative here. Now we're getting into the moment. So in this case, the only direction that allows for rotation is the x-plane. So we're going to go ahead and assume that a rectangular application of force is being distributed with the wind. Therefore, the applied point will be at the center of mass, which is half the length divided by 2. So if it's the length divided by 2. However, we still have to take into consideration how the bracket system works. So the load is being applied onto a 2x6, onto a 2x6. So in order to find the moment which is being generated, we're actually going to take half the center of the 2x6 and then find the distance from there to the actual center of the sign. So if I go ahead and show you right here, these brackets actually lie at the center point or at the halfway point of this distance right here. So if the 2 by 6 were to be here, the distance which we would find it would be this exact half point to here. So after you go ahead and calculate that, it's actually 0.25 feet or uh 3 inches, if I'm correct. I believe so, sorry. And then that's how you find the moment. So the moment is going to be 90.475 pounds feet. That's the moment that's being applied, I guess, due to the force of the wind. So the reaction moment just ends up being the exact same, but of course, in the negative direction, which I forgot to include here, but just keep in mind it's in the negative direction. Now these are my two references. One which I used to go ahead and find uh, the highest wind speed recorded here in El Paso, and the other one which I used to go ahead and find the force of wind applied on a certain object. That concludes my presentation.